Okay, so we're continuing our discussion on the Newton-Raphson algorithm. In this video, we're going to focus particularly on the use of Newton-Raphson on logistic regression and solving the maximum likelihood estimation for logistic regression. Um, Particularly, we are actually going to start focusing in this video on Newton-Raphson in higher dimensions. So this video and the next one will be on that particular implementation. So our previous function, objective function, was a unidimensional function. So for example, in the last video, we looked at the likelihood that is coming from a consequence of the location Cauchy distribution, where this is the likelihood as a function of mu, and mu was in R, which means that the parameter space was one-dimensional. Okay, and then as a function of mu, you have a likelihood or a log likelihood that sort of takes some shape. It could look like this. It could look really, really, topsy-turvy, or it looks something like this. Now, if though we have multiple parameters, so we have, parameter theta 1, theta 2, up to theta p. So our parameter space theta is p-dimensional. So if p is 2, I basically have, some space indicated by this curved space that is my parameter space. And on this particular parameter space, this sort of curved parameter space, I have a third dimension that takes the shape of the function on this bounded space. Okay. It could be a bounded or an unbounded space. That depends on the parameter space. But theta over here defines a p-dimensional space, and the function lies on top of that in the p plus first dimension. Okay, which means that if I have, a parameter space theta 1, theta 2, let's say, then I want to find that particular tuple, that particular theta star 1 and theta star 2, that together gives me the largest value for the function over any place. Okay. So that is then our objective function. I realize I haven't written it here. So the objective, the problem I want to solve is still theta star, which is the argument that maximizes some function f theta. Okay, it's still the same problem. The only difference is that now theta lies in some we can say for simplicity RP, or theta lies in some set, let's say capital theta, which is some subset of RP. Okay, that's really what we're looking at. But then in this space, what becomes really important to keep in mind is that if we want to do the Newton-Raphson algorithm, then I know Newton-Raphson will look something like this. Newton-Raphson looks like, the iterates look like theta k plus 1 is equal to theta k minus f double prime theta k inverse f prime theta k. Right? But now the question is, what is f prime theta k? What is the first derivative with respect to theta? Well, and what is the second derivative? Well, when theta is one-dimensional, the first and second derivatives are all one-dimensional. However, when theta is p-dimensional, the first derivative now becomes a vector. So gradient, which is denoted by gradient of f. So gradient of f is nothing but f prime. Okay, f prime is gradient of f, which is basically the vector of all the partial derivatives. So the first component of this vector is going to be partial derivative of f with respect to theta 1. The second component will be partial derivative of f with respect to theta 2. And the last component will be partial derivative of f with respect to theta p. And this is now a vector stacked up, a column vector. Now, so that's the first derivative. Now the second derivative is basically your f double prime. And your f double prime is what is denoted as nabla squared. So this is nabla f and this is nabla squared f. Okay, and then this quantity over here is also called the Hessian or the Hessian. Okay, so I'm going to often denote and call this the Hessian as well. And the Hessian in this case, the second derivative of f, is now going to be the pairwise second derivative of all of the elements of theta, of f with respect to all pairwise combinations. So over here, I take another derivative of this with respect to theta 1, theta 2, theta 3 up to theta p. So I go del square f by del theta 1 square, so that's theta 1 again, then theta 2 going up to theta p, right? So the partial derivative squared of f with respect to partial derivative of theta p and then theta 1, right? So, and then we have all of those filling in the matrix over here, and this gives us finally a p by p Hessian matrix. Okay, now this obviously is also going to be a symmetric matrix because del squared f by del theta p del theta 1 is equal to del squared f by del theta 1 del theta p. That's just by our understanding of partial derivatives. Okay. Now, the main thing to remember is that for a Newton-Raphson algorithm, we knew that when f double derivative was negative, when f double prime was negative, we had a concave function. But now the question is, now our second derivative is a matrix. So how do we know if a function is concave? Well, we know that the function is concave if the Hessian, the nabla squared f, or the second derivative, is negative definite. Okay, so if we know that the matrix is negative definite, then we know that we have a concave function. So when is a matrix negative definite? Let's write that down. Matrix A is negative definite if for a vector A non-zero in P. So if I take a non-zero vector A in Rp, then if A transpose I should not have called it A, is less than equal to 0, okay, then A is negative semi-definite. Okay, else, not else, sorry. And if it is less than 0, then A is negative definite. Okay. On the other hand, we already know what is positive definite. So matrix A is positive definite if for, now let me be wiser and say B in Rp such that B is not equal to 0. If B transpose AB is greater than equal to 0, then A is positive semi-definite. Okay. And if B transpose AB is exactly greater than 0 for all B, so let me say for all B, then A is positive definite. That's just for us to understand what positive definite, positive semi-definite, negative definite, etc. mean. Okay. Okay, so this is basically where we were. So if we want to know whether an objective function is concave or not, we find its Hessian and then we check if the Hessian matrix is negative definite. If it is negative definite, that is, it satisfies this, then we know that it is a concave function, and so we know that there exists a unique maximum. We'll see an example of this today in this video. Now the question is, how do we actually do the Newton-Raphson iterates? So I'm not going to show the sort of origination, but the idea is similar. Instead of taking a unidimensional or a univariate Taylor series expansion, we do a multivariate Taylor series quadratic expansion, which is very similar to the univariate. And you can see what happens if you basically do, in a multivariate function, you do an approximation that is a concave quadratic approximation that is a bowl in p dimensions, and then you find the maximizer of that bowl and you keep doing it sequentially. Okay, it could be a maximizer or a minimizer based on what kind of a bowl is constructed. Okay, and the optima of that bowl, where the maxima or minima occurs, is going to be your next iterate, whose formula is then given by this update. Okay, and now over here you have, this Hessian f theta k inverse needs to exist. So if Hessian f theta k is invertible, then you can do this. Sometimes it won't be invertible, so you won't be able to do this. Okay. And notice that this update looks quite similar to this update, right? So this is a multi-dimensional update, and this is a unidimensional update. They're very similar, except you can't really do a division over here by a matrix, and so you do a matrix inversion. Okay, so this is how the Taylor series approximation can be used to develop potentially the Newton-Raphson algorithm in higher dimensions. What does the actual algorithm look like? Well, it's very similar. Now you choose a starting value for theta 0 and you choose a tolerance epsilon. Okay, so theta 0 and epsilon, just like before. And then for any k, right, for any index k, the next theta k plus 1 is going to be theta k minus this the inverse of the Hessian at that theta k times the gradient vector. Okay. Now I know that at the solution or at the optima, my gradient is going to be small, it's going to be very close to 0. So I can measure when my gradient is 0, I can stop. But the gradient, recall, is not a number, but it is a whole column vector. So instead of looking at every element, what we can do is we can look at the norm of the vector, so norm of the column vector, and if the norm of the column vector is less than epsilon, then we say, okay, great, let's just return this iteration and stop. Otherwise, we continue on to step number 2 over here. So we keep doing this until the gradient value is actually small. Okay. This is the idea of the multivariate Newton-Raphson algorithm. Okay, but let's actually see this for implementation on a real setup. So I'm going to pivot now to logistic regression, which is where we are going to be using this particular multivariate expression. Okay, so we're going to do that in the next video.